Assalamualaikum warahmatullahi wabarakatuh. For today's lecture, we are going to continue on structural steel column design, the second part of column design. We are going to look into the compression checking and also buckling checking for steel column. For the first checking, we are going to check for compression resistance of column. Compression members subjected to an axial load are susceptible to flexural, torsional, and torsional flexural buckling. To determine the compression resistance, the formula is given here according to EC3, class 1, class 1. And for class 1 to class 3, you have to use NCRD equals to A times Fy divided by gamma m naught. And for class 4, you need to use effective area, since class 4 is the elastic condition of the column. And you need to make sure that NCRD or compression resistance is greater than the axial forces applied to the column. So then if the ratio between NED divided by NCRD is less than 1.0, it means that the checking is passed. So in the appendix, it's given in page 12. So look into page 12 to find the compression resistance equation, which is NCRD equals to A times Fy divided by gamma m2. A is the cross-sectional area given in the appendix based on your section designation or size. And you need to make sure that the classification of the column should be class 1, class 2 or class 3 so that you can use this equation. Okay, next checking is on the buckling resistance. The overall buckling resistance of a column is given in clause 6.3.1.1 from EC3. Based on class, for class 1 until class 3, NBRD is equals to reduction factor times area times Fy divided by gamma m1, and this value should be greater than the applied axial forces. And the X value is the reduction factor for the relevant buckling mode, and we need to determine what is the X value. In appendix page 13, this is the equation for buckling resistance. Here is NBRD times X times A times Fy divided by gamma m1. For buckling curve, since the value of reduction factor is unknown, so we need to identify the X value. It's given in appendix page 14. The X value is this equation. And in this equation, we have two unknown value, which is the phi value and also the lambda prime value. And it's given that the phi value, the formula for phi value is here. And in the formula, we have alpha value. Alpha is actually imperfection factor given from table 6.1. And also in the phi equation, we have lambda prime value. It's given here that the lambda prime is equals to square root of A Fy divided by NCR. However, the value of NCR is unknown, so we cannot use this equation. Okay, we are going to use another equation to calculate lambda prime. Here is the table 6.1 for you to get the imperfection factor for buckling curve. The buckling curve, here we have 5 different type of buckling curve. So first you need to identify what is your buckling curve of the column. Then later we can get our imperfection factor alpha. And to get the buckling curve, we are referring to next table. Okay, this is table 6.2 for selection of buckling curve for a cross section. Since we are going to design a roll section column. So we are going to use the first row here. Right, the first thing that you have to do is to check the H/B ratio, whether it is greater than 1.2 or less than 1.2. Then you check the value of flange thickness, TF value, whether it is 40 mm or less, or in between 40 and 100 mm. And then you need to identify the buckling about axis, which axis that you are going to check for buckling, whether you check for major axis YY or you check for minor axis ZZ. Okay, let's say we have a TF less than 40 and we are going to design buckling about ZZ axis. So, and then you can get the buckling curve B. Or if you check for YY axis, then you can use buckling curve A. Okay, it's depending on your buckling axis that we check. Then we can identify our imperfection factor alpha. Alright, so a real column has geometrical imperfection and presence of residual stresses, which is stresses that develop in steel section during the production. Okay, so the steel section have a small imperfection. In real column, buckling occurs when the column slenderness is very high, as defined in the slenderness as. Since the value of NCR is unknown, we also can get the value of lambda prime using this equation. Okay, instead of using NCR, we can also get the lambda prime is equals to LCR divided by I is radius of gyration here, times V1 over lambda 1. This is for class 1, class 2 or class 3. Okay, and what is LCR and what is lambda 1? LCR is the buckling length in the buckling plane considered, and I is the radius of gyration of the relevant axis. Let's say you check buckling resistance about ZZ axis, then it means that I is in ZZ axis. Okay, the I value you can get it from the appendix, the property section. And you can calculate your lambda 1 using this formula, 5 times square root of E divided by Fy. E is the elasticity of the steel. Or you just can use this equation, which is 93.9 epsilon. So you can use either one. Okay, and LCR, we take the value of LCR depending on the support of the column. So the buckling length LCR is taken based on previous solution. The end restraint could be referred to table of buckling length extract from EC3 page 7. So end translation restraint or pin restraint also called restraint in position in the table. And if end rotational restraint or moment restraint also called as restraint in direction in the table. Okay, so we are referring to this table. In your design appendix page 70, we have E or LCR. So end restraint in the plane consideration, it means that it's hold in the position. Effective, the condition is effectively held in position at both ends. So it means that the both end is in position. And if you have buckling length for effective restraint in direction at both ends. So this means that at both ends it is fixed condition. So you use LCR equals to 0.7 L. If you have partially restraint in direction or at both ends, or you have restraint in direction at one end, and another one is fixedly restraint. So it means here is pin fixed condition, and here is partially restrained, which is some kind like a spring. at your end. So you can use 0.85 L. L is the height of the column. Or not restrained in direction at either end is pin condition, when you can use buckling length is equals to the height of the column. Okay, so the condition is taken from this diagram for non-sway mode of column. Alright, let's revise. How do we calculate the buckling resistance for columns? So here is the step-by-step procedures, the summary of the procedure. So the first thing that you have to do is you need to identify what is your buckling axis. Which buckling axis that you are going to check. So normally we check for critical axis or weak axis, which is minor axis, ZZ. Or we can, if we have the column section with different height in terms of their axis, so then we can choose axis with higher length for you to start the buckling resistance checking. Since higher the column size, it will be point to buckling as compared to the short column. The second one is you need to determine the effective buckling length in axis to be considered. Let's say you are checking ZZ axis, then you need to check what is LCR in ZZ axis. And what or you want to check in YY axis, then you need to know what are your LCR in YY axis. So it depends on your support condition of the column. So let's say you have pin, or maybe you have intermediate restraint at the center, so you need to check based on the axis. Okay, and then you find your lambda 1 value using this formula. And I radius of gyration can be taken from the appendix, properties of the section. And you need to make sure that the unit is mm. In the appendix, the unit is actually centimeter cube. Then you have to convert to mm cube. Okay, so once we get our lambda 1 and radius of gyration and LCR, then you can get our lambda prime value. Okay, so next is we need to identify what is our buckling curve based on table 6.2. To use this table, first find H over B value for the limit, so that you know you are going to use the top row or the bottom row. Check your TF value and then buckling axis. Then you can get your buckling curve based on the steel grade. If the steel grade is lesser than S460, then you can use this column. Yes, once we get our buckling curve, then we can identify our alpha value, which is imperfection factor is much depending on our buckling curve. For example, let's say we get buckling curve B, then our imperfection factor is equals to 0.34. And then we can calculate the phi value using this formula. Substitute the alpha value and lambda prime value. Once we get the phi value, then we can calculate what is our reduction factor. And we need to check whether the reduction factor is less than 1. Cannot be greater than 1. If you get greater, then it means that our reduction factor is equals to the limiting value 1. Okay, once you get your reduction factor, then we can calculate our NBRD buckling resistance. Reduction factor times AA is the area of the section, and Fy divided by gamma M1. And we need to compare with our NED. The ratio of NED over NBRD should be less than 1, so that the buckling resistance check is passed. Okay, so that's all the design procedure. From previous class, we have covered on how do we determine the ultimate design axial force for column, and then the selection of section, classification of section, Then you need to check resistance against compression and also resistance against buckling. Okay, so here is one exercise. So you need to check the suitability of the column, given column size here. If the section is supporting a compression force of 1,400 kilonewton, you assume that the column is pinned at both ends and that the height of the column is 6 meter. Okay, the applied forces NED value is 1,400 kilonewton, and the condition at the top and bottom is pin, so means pin condition, and the height of the column is 6,000 meter. Okay, here is the axis. The axis, ZZ axis or minor axis will cut through along the web, and YY axis should cut through at the center. Alright, thank you very much. So I will see you on the next video on how do we solve for column design. Okay, thank you.